Yeah, so I appreciate the chance to speak to you at the end of your planetary mapping winter school. And I appreciate the chance to wrap up in a certain way. And, please bear with me because it is 7 o'clock in the morning here and I just woke up on the West Coast of North America. So again, thanks for having me. But I'm excited to talk about some new ways to think about doing geologic mapping. And you in this school have already experimented in this direction because some of the tools you have been working with in QGIS, such as MAPI, the tool that was developed to maintain topology for geologic maps, goes in a very forward-looking direction for creating geologic maps. But here I'm going to talk about some visions for software and some prototypes and early versions of software that will go further in that direction. And because this is kind of early days, I was hoping to do an interactive demo that everyone could participate in briefly, but that didn't quite come together. So you'll have to bear with me as I describe the project and then show some brief video demos. So I will be talking about making geologic maps, which you have been doing for most of this week. And I'm a structural geologist by training, and I did mapping on Earth and Mars during my PhD, which I finished about 3 years ago. And since then, I have been working at Macrostrat at the University of Wisconsin. And for those of you who have not heard about Macrostrat before, it's macrostrat.org, the website. And it's a global compilation of geologic maps and stratigraphic columns, all layered together in a multi-scale product. So this is one view of what we are, the data products we compile here. And these are from US Geological Survey and other geological survey maps of Earth. And we work to compile those into a standardized data system. And one of the great things about this data system is once you compile maps and put them on the web, they can become a product that can be used collaboratively in many different ways. And so not only are maps available on the website, Macrostrat, and also can be pulled into GIS, QGIS layers can be extracted from this to stream from the web as well. But we can also showcase them in mobile apps. So we have a mobile app that we've developed that shows you the geology near your location. And then many other mobile apps developed by other people have shown geology using our layers for various purposes. So I'm basically working on geologic maps, hopefully covering the entire world, which gives me an opportunity to work on kind of the technical cutting edge of how we package up geologic maps and deliver them to various devices. And as part of that, I'm also working on new ways to make and visualize geologic maps, which is what I'm really going to talk about here. And part of that includes putting geologic maps on new backdrops, such as 3D digital globes, like you see here. And this isn't really the subject of this talk, but this is just a preview of things that are coming in the future. So hopefully we'll have streaming map products that are overlaid on something much like Google Earth and can be explored with geology. And part of my work has been targeted at Mars as well. So basically, hold on one second. Yes, part of my work has been targeted at Mars. And basically the idea is once you have a set of techniques that works well on Earth for representing packaging and um, collaborating on geologic maps, you can also use that for most Mars mapping tasks. And that should be familiar to you since you have spent most of this week using software QGIS that was developed for Earth use to do great things for mapping in planetary settings. So this is an early example that we're actually using Mars as a test bed for new things that we are trying to develop on Earth, such as showing geologic maps from individual sources coming out of our data system at one or individual maps separately instead of as a streaming layer. So this is the map of the US Geological Survey map of the Jezero Crater Delta near where Perseverance is currently searching for fluvial deposits. So we've done a lot of work at Macrostrat, and our main role there is to showcase geologic maps created by the community in general for various purposes. But what we're going to be talking about here is actually creating geologic maps and using some of these same web-based streaming techniques to create new processes for creating maps. And so the first thing to keep in mind here, in terms of how we think about how we want to create geologic maps, is that we have devised over the course of the 20th century a really remarkable process for synthesizing geologic knowledge. And so the technique of paper mapping is one that is hundreds of years old and has reached kind of a zenith of being a really wonderful way to represent data. And so this is a classic geologic map of the Grand Canyon that uses the color gradations and the topography together to show in great detail the form of the sedimentary rocks and the underlying basement rocks that make up the canyon. And so we've done a very good job of creating processes to create geologic maps. And there's a challenge in making those processes map well to the digital world. And so that's kind of where I came into this, was as a PhD student about 7 years ago or so, starting work in two regions. And so these are two areas at about the same scale, roughly 100 kilometers on a side in southern Namibia in Africa and northeast Syrtis Major and Mars. And these were areas that were important to map for various reasons. On Earth, it was a fold and thrust belt project that was important for the Cambrian boundary. And on Mars, it was near the potential landing site for the Perseverance rover and hosted thick sedimentary deposits, which are these sulfate deposits in blue on this map here. So two very interesting mapping projects to accomplish during a PhD, but not a very good idea of how to accomplish them going in, which I think is a common experience for many people when they start out mapping, especially if you're mapping a reasonably large area, is not knowing what to focus on and how to attack the task. And what I've kind of found over the years since I started this was that the best way to attack a mapping task is in an iterative way, which means basically you try to map it once, you map it, but with some inconsistencies and some failure, you go back, you refine your map, you correct deficiencies, you continually move forward. So it's very unlikely in a complex region that you will make a very well formulated map the first time around. And so what needs to happen is essentially a process of continual and gradual refinement. And for me, this was erasing and redrawing a paper map, but it is trickier in the digital mapping space. So what I will do is then now take you through an example of my field project on Earth, which was really the genesis for thinking about new mapping techniques and ways to solve this problem. So we're looking at the Naucliffe Nap complex in Namibia, which is a fold and thrust belt nap that basically the hanging wall defines a mountain range. And you can see at the midpoint of this picture a basal thrust fault that's almost planar with imbricated dolomite blocks above and sheared limestones and sandstones below. So this is the Naucliffe Nap complex. It's a relatively famous mountain range and was a wonderful place to map. And it has a long heritage of being mapped on paper very effectively. And so the first map of this mountain range was created in the 1950s on a very large sheet of vellum, as was typical at that time, and rendered here in abbreviated form in a GSA bulletin paper. And here is my attempt at synthesizing a brief tectonic map just in my field notebook of the naps. And so it is very easy. This is something I drew over the course of about 20 minutes or so. And it is very easy to capture a lot of information by drawing it on paper. It's a very expressive medium. So that is what we're up against, is paper, which works quite well. Then the other problem that I started thinking about as I started mapping was, what scale could I map at? And so this is kind of an example, just zooming in and panning around the 3D map here, that shows that the mountain range is large, about 60 kilometers on a side for my mapping area, but there is structure at high resolution. So a lot of the most relevant structures are about 100 to 500 meters across. So to capture the folds and thrusts that really make up the bulk of the interesting geology of the nap, we needed to zoom quite a ways in. And this presents a problem for paper mapping in the field. Basically, we start with these field sheets that capture the relevant detail. So a typical one would have about 4 kilometers on a side. So, you know, each box in this view on the right would be 1 kilometer square. And you would have as many of those as you need to cover your field area. But for me, that was about 30 map sheets. And I spent a lot of time in my initial mapping seasons switching between map sheets and trying to keep track of what I had mapped where. It's just untenable. And that was magnified by the fact that to map this mountain range well, we really needed to drive around and go to different places. So, you know, I would be changing map sheets every day or two. So this paper workflow wasn't really ideal. And the frustrating thing is that it wasn't enough, because geologic maps end up as digital products in the end. So this is just what the map will hopefully end up looking like, is something that can be zoomed in on a computer in GIS or operated on in a database. And so you have to first map it on paper to do your field mapping, and then you translate it to GIS. And what that ended up with was me trying to keep up with this and charging my battery in the truck by day and clicking points on my laptop to try to digitize the day's mapping for hours by night. So that was not an ideal workflow, and that kind of created the need in my mind for something better. not just for the process of creating a final digital product, but also for capturing an initial map. And so there is a big difference from how we would like to map and how we map on paper and how we currently map in GIS workflows. And so on the left, what we're seeing is kind of the ideal situation, which is that we can draw lines, we can erase them, and the topology of the map kind of follows along with us as we quickly assemble it. So we can see the map as we're creating it. And traditionally in GIS, the workflow is very different, which is that you draw all of your lines and then you digitize the topology, which usually involves the ArcGIS model builder or some equivalent, and is a very tedious process involving mostly dialog boxes. And it's clear that this needed to change because it wasn't conducive to high quality mapping. And so I'm not the only one who realized this. Luca and others over in Italy have also come up with the MAPI tool, which does a very similar thing of iteratively solving your topology from your boundaries of the map. But that is one key advance that is needed for mapping fluidly in the field and in the lab. The other advance is much less of a invention of geologists and just a background condition of the world, which is that around this time, the technology for stylus-driven computing really took off. So in 2016 or 2017, I think, yes, 2016, the Apple Pencil was released with the iPad, and that was like an advance that made new things seem possible in terms of mapping, because this was an accessible device that could potentially be used for drawing. So that was a pretty big advance that spurred on new ways of doing things. The second advance was just one that you're getting increasingly familiar with in this class, which is essentially that open source GIS software has gotten better and better over the years, and particularly the PostGIS spatial database and the QGIS user application for dealing with GIS have become much better and more able to be worked with to do interesting things. So a lot of the work to follow has been driven by this GIS advances. And so what this has led to was building an iPad app that interfaces with the GIS software on the computer to build maps by drawing them. And so this is an example. Oh, that was supposed to be a video. Maybe play. Well, we don't have the video, but we'll see the app in action in a second. So, oh, there we go. So this is a video that basically shows the key features of this app. And one thing to keep in mind is that this workflow works in QGIS as well with the iterative mapping approach. The app just provides a quicker way to draw lines. And so basically we can add data to a GIS database from the iPad directly using natural editing. And the result of this has been basically the ability to make a very high quality map that has a lot of detailed line work by drawing it in GIS instead of manually adding points. And so this could be done using other devices such as Wacom tablets to do streaming digitizing, but the iPad is a particularly natural user interface. And here's another view of the high resolution structure of the map, which shows that we can capture folds at a few 100-meter lateral scale pretty well, because we're able to quickly and easily draw into GIS. And this is what it looks like in the iPad at the point of creating the map. So I'll do a brief technical explanation of what we are, how this is constructed now, and then we'll look at it in action briefly. So what we have here is basically a system for tethered mapping. So there is this Mapboard GIS iPad application that sits on a computer on the iPad and is attached via Wi-Fi to a server, which is running a PostGIS spatial database with a small networking component in front of it. And that spatial database handles the task of actually creating GIS records for the lines that the iPad application is digitizing. And because this is a standardized spatial database, it can actually be read in real time in QGIS and in slightly less than real time in ArcGIS. And this enables collaborative mapping between multiple iPads potentially working on the same mapping project and multiple people working in QGIS. So it's to be emphasized that the iPad is part of this system, but not a necessary part. You could be using this topological mapping system just with QGIS and PostGIS as well. And so this enables us to have large data sets streaming into the iPad for mapping locally. And there's an open source server component that sits in front of the PostGIS database and optionally handles the topological mapping as well. And so with topology, to actually manage the topology in a way similar to mapping, we use an iterative approach that uses this PostGIS geologic map software that basically watches for changes in the PostGIS database and takes data out of this map digitizer schema, which has raw mapping data, and moves it to the map topology schema, which has the solved topological map. And so this is an open source component that we are developing at Macrostrat, and hopefully soon we'll use in our map production pipelines for the global geologic map compilation I showed at the beginning. But this is essentially fulfills a very similar role as the MAPI project, but it's for collaborative mapping on a server instead of a part of the QGIS user interface software. So now I will briefly switch to my iPad and attempt to show you a demo of this in action. So here is the iPad screen. And now I am going to open up Mapboard GIS here and navigate my long list of testing projects and find this project that is called Nowcliff Remote. And judging by the lack of data here, I am going to ensure that, oh no, it's filling in. It's easy to forget to turn the server on when I am running it on my own computer. So we're starting to see geology fill in. It's a lot of data, so it comes somewhat slowly. But we eventually get a map that is being built. So this is a similar map that you would see in QGIS if you were to load this project. And right now, the fault tick labels in this app are very oversized, but we will ignore that. And what we can do is just take a sample and draw some new data in. So we can choose a line type and say we want to draw a bedrock contact. We can just pick an arbitrary place to draw our contact and start drawing lines naturally. and the line should appear once it has been inserted into the GIS database. And so if I then draw another line that crosses some topologic areas, it should actually cut that topology and cause two new topologic segments to be created. Although sometimes it's necessary to reload the view to ensure that that shows up. Another thing that we can do, because this is a multi-scale system, is we can just move to another place on the globe and try creating new mapping in a separate area. So this is I've moved a little bit to the south, and I'm just going to, for illustrative purposes, create a bedrock contact here. There. I didn't have the live topology on, which is part of why it was not reloading. So here I'm going to make some quick lines. And then I am going to fill them in with a polygon. So I'm going to arbitrarily call this, I'll just pick a unit here and fill in a polygon. Maybe that didn't actually hold. That did finally. Okay, so if we scroll over to this topology watcher, we can see that the topology is being updated. New rows are being created. And now if we go back here, we can see this has filled in. So this is a similar process that you have done with MAPI, but is being done in real time on the server. And I apologize for how slow this is being right now, but it is slow, but reasonably effective. Okay, so that's a basic demo, and we'll do a planetary demo in a second. But now to continue with discussing what works for Earth generally works for other planets in the GIS space if we're able to deal with coordinate system transformations and different imagery base layers and that sort of thing. So evaluating it for Mars was important for me because doing my other mapping project was on Mars. And so this map of Northeast Syrtis Major Mars was actually an interesting case study because I developed the app primarily for working with my other map on Earth. And I was doing a reasonable job of mapping Syrtis Major just using the mouse and QGIS, but I actually very quickly remapped the entire area using the pen-based approach because it was so quick to make adjustments. And then I was able to make continual refinements much easier than I would have been had I been using a more traditional approach. And so I will now shift to quickly doing a demo of the planetary mapping mode in Mapboard. And I hope this will work a little better because the planetary data set that we're working with currently is not quite as large as the Nowclift mapping data set. So here we'll go to Aeolus Dorsa on Mars, which is an area that one of my students is currently mapping using this software. And so again, we have layers streaming in, and while the Namibia map is running locally on my computer, for this map, the server is actually running at University of Wisconsin on a server. So this is publicly accessible if you were to have the right credentials, and this has allowed my student to map from home while I can see her work and look at it in this interface or QGIS. So what I'm going to do is just go over to the side here where we have unmapped area and create an example little map. And so this is a bedrock trace that we are adding here. It's pretty fluid to add new traces. And if we zoom in here, we should see that the edges have snapped together. That's one feature of this software. Let's make sure that we have the topology, live topology on, and just in case we'll reload it. And then what we can do is we'll pick from our list of units here. And so we can say this is unclassified too. And draw a polygon to denote that we have decided what that unit is, and then continue moving. Oh, and that polygon fills in. And so if we draw another polygon for a new unit that's adjacent to this, then we can basically fill this in with a different thing, although there's a small bug here. So we can call this late channel deposits, even though this is obviously incorrect, and that will eventually fill in. There are also tools that should be familiar from QGIS, such as reshaping line work and other pieces, so we can modify the lines that we have created already in a somewhat quicker way. And then this should hopefully reload, although we can help it along sometimes. And it will create a nice looking map for us. So one of the things that I unfortunately cannot demo today is the process of doing this with many people contributing to the same map. And we have done this successfully in some cases, but it gets a little bit slow. So one of the things we're working on is doing this more rapidly and fluidly in a collaborative setting. But one of the other pieces of this that's important to mention is that this integrates very well with QGIS. So a lot of the workflow pieces that you have learned over the course of this week for working with QGIS are very applicable still to this new collaborative workflow. So if some of these elements should be implemented in your mapping workflow, you can then look at your map in QGIS, do all of the production steps in QGIS, and see things streaming in real time. So just as an experiment, I am going to make a change while you are looking at this QGIS view and just reshape one of the polygons here. And we should see that change. This was a change made on the iPad, but it snaps out very nicely. And I can in fact make a change in QGIS and the same thing will happen, or should. So let's just divide this in two here and have to make this the type be bedrock contact, which should autofill. Or no, maybe that's default. I don't know. Thought this would autofill, but perhaps it won't. So we can look at the attribute table here. That is what the attribute table says. Okay. Huh. Okay, should auto set this ID, but it's not, so it's okay. Oh, you know what? This is the wrong layer, so that is why it's not working. So we will just not save this and not worry about editing it in QGIS, but it does work. Actually, let me just add the layer here quickly. In the last few minutes I have. So okay, so we'll add this map data. And it's complaining about the spatial transform, but it does appear to show up. So this is the actual line table that is being used in the GIS topology calculation. So here I can add a line to this table, and yes, it has an auto-generated key, and then I'm going to say and once I save this, it should go into the database. And you can see the topology starts to regenerate. And then on my iPad, I can go in and create a polygon just for speed. And I'll call this an alluvial fan deposit, even though that is obviously incorrect. And we should see that turn pink. So this is a system that can be used on multiple devices simultaneously and by multiple people at the same time. So this is what it looks like on here. In QGIS, this is what it looks like on the iPad. So this is a pretty cool new capability that we're building, and it's obviously in early days with a lot of frustrations, but there are a few different things to mention kind of at the end of this. One is that there is also a mode that allows you to map on the iPad in a standalone mode using a onboard spatialite database. And so that gives you some of the topology benefits while you're mapping in the field, although it does take a lot of battery power to use. I've already given a demo. One other thing to note is that this uses streaming base maps to work on the iPad. The iPad doesn't have as powerful of a GIS engine as QGIS. So we have to use base maps coming from the web. And I know Trent talked about that yesterday, but there are lots of options for base maps that we can use. And we're actually working on devising other ways to, or ways to pull in high resolution base maps easily into this mapping platform, because that's a key need for moving, for being able to map high resolution areas. And finally, next steps for this tool and technique are a lot of performance fixes and optimizations for the iOS app that drives this. You know, fixing bugs, making things quicker, making the network calls respond faster, so it is a more fluid user experience. And the other part is to create an easier workflow for getting started with this in QGIS. One of the things that MAPI does really well is integrating well with current GIS workflows. And this is not at the point where it does that quite well. So one thing we're hoping to do, especially in collaboration with folks who want to use the tool, is to create better workflows for QGIS and other GIS integrations here. So I would encourage you, as members of this workshop who are going to do some mapping, to check out the app and ask me questions about it if you're interested in using it, and to think about ways to integrate the topology solver part of this in your own collaborative mapping projects using QGIS or any other platform. So I thank you for listening to this talk, and I hope it is a good end to the mapping school, and I'm excited for all the things we will get to map in the future. So thank you very much for your time.